coronary intervention, concrete PCI.
Xin lỗi, em ghi lại cho mấy bạn không hỏi một xíu nha. Cái này là ghi lại toàn bộ. Lát nữa nếu mà thấy anh bấm vào stop share ở trên này, xong rồi anh chọn cái mà xe
Mention to each other to see which of them is better than the others. So let's look at the Excel file here. We have you will say that we will have in total 4 comparisons. We will compare complete versus complete, complete to stage PCI, complete PCI to immediate PCI, and complete PCI to complete. So it's overall 4 comparisons. Okay, so let's start the CMI software. The first thing you want to do here, you go to insert, column forms and study names. The column study name will appear, and here you will pass on the study on the study. You want to make the meta-analysis in here. Okay, let's copy on this study. So here we have 15 different studies. We will say that some study has account for several rows because in that study we will have many small subgroups. So that is a column for subgroup listing study. The subgroup within study we want to consider here is the time of follow-up. One study will have different kind of time of follow-up. For example, the first study here, MS1, we see that they check the result of the many different kinds of outcome at a different kind of time of follow-up. 24 hours, 30 days, 1 year, and 4 years.
Anh ơi, anh bấm vô stop share cho lại đi. Ở trên đó, ở stop share trên. Rồi xong bấm vô share screen. Share lại.
Time of follow-up. The point of subgroup comparison is that we want to compare the outcome of the same time of follow-up, or at least near that one single point of time as possible, so that our result is not biased by different kind of time points. So here I want to copy the name. We go to insert, column for effect size data. One of the most useful thing is CMA software is that it contains a lot of different size effects that you can choose. For example, in here I want to compare two groups to each other. In this situation, I want to compare the complete PCI group to the complete PCI group. So I will choose the comparison of two groups, time points or exposure, including correlation next. The case that I want to perform the meta-analysis is the customers because of number of events, how many deaths we record in during the after the BCI's intervention, and match group, event rate and sample size in each group. Okay, so finish. So group A, you will rename it as country, and group B is complete. It is two interventions that we want to compare to each other. Okay. So now we have two groups right here, events and total. Go to the Excel file, the data file that you prepare, and copy all of them. So here's the Excel file that I prepared to perform the analysis. You copy all of these information in here. Copy. This is the outcome that I want to compare the overall major adverse cardiac events. So I want to copy it to the series. And complete it. Copy the password. Can you say that the CMA software will automatically calculate the odds ratio for you in the yellow column? So now we want to perform the meta-analysis. Let's run analysis. Of the study, we want to compare to each other. We want to put the risk ratio will appear in this column. And with different subgroups. Okay, you see that one study will have different subgroups based on their time of follow-up. What I want to do here is I want to pick out the most pick out the same time point so that I can compare to I can consider this situation when our results right here is significant. If the result is significant, we have to look at the sensitive analysis to see that if you look at right here, one study removed, you look at the p-value of one study right here, you see that all the p-value of this study is below 0.05, then it's okay because removing one we study will not affect our significant result. But if one study is over 0.05, then you know that that study is kind of remove that study is kind of affecting our result, which means that study may have a larger population. It influence a lot about the other study. The strength of that study is more powerful than other studies. So it plays a very important role in our significant results, and maybe it's a bias to others to our Bun's risk ratio right here. So that's the utilize of sensitive analysis. In this case, our result is not significant, so we don't have to do this task. So you may perform the publication, the meta regression with publication years. You can also perform it with other factor that you can consider as maybe it's a confounder, and you want to see if it's influence your result. You can look at, for example, I will perform the meta-analysis with the proportion of the male population. Okay, and you calculate the population of the male people in this in all of those studies.
Anh quay đi, em đang livestream. Thôi em tắt cái livestream đi. Ý là em muốn quay lại cái màn hình laptop này luôn nè. Quay lại cái này này, các bạn sẽ dễ thấy hơn. Mẹ không biết làm sao để cho thấy.
Wait a second. Total number of patients. Okay.
Ủa sao cái gì kỳ vậy? Quay vậy sao thấy màn hình?
Cái này quay màn hình sao? Em nghe mấy còn có
Thôi em ngồi đây nữa đâu. Em quay nữa đâu.
không muốn bị nổi tiếng.
Trời ơi sao nó kỳ thế?
Sorry for this convenience. I forgot to calculate the male population, the total number of male population. But let's assume that we have the proportion of males population in this column. For example, you have here 111 in the complete group and 108 in the complete group. So we have total here is 219 patients in the total population, and the males is 50. So the proportion of male population is 50 over 219. So you will create here a column property. You will create a column for male proportion. The column function will be as a moderator, and we choose that data type as decimal and OK. I will just create a random proportion. 40, 59. study from multi-regression to proportion of male population. You see here is the coefficient of the male of the meta-regression of the male population, the male proportion of the population minus 0.004, and the p-value is 0.98, which is over 0.05. So the male population does not have any influence on the size the result of our meta-analysis. But if you have let's look at the regressions, the log the graph right here, you will see that most of our results log risk ratio belong to the middle of the performance around 50%. So this means that whether the study has this study has the number of males and female in this study does not have any bias on the risk ratio that we pulled from 10 study.
Nó còn là subgroup analysis, subgroup rồi total, em có làm đó chưa?
Subgroup này em nói.
Subgroup nhưng mà subgroup total chưa subgroup rồi pool together.
Cái đó thì không có đặt total cho subgroup.
Nó không có data. Rồi, xong hết rồi. Còn gì nữa?
Analysis again. Okay, so here is a significant analysis that I have shown. We have the pool risk ratio is 1.66, and the p-value overall is 0.025. So our result is significant. The pool risk group is not better than the complete group. So now I want to perform the sensitive analysis. Pick one study removed. So here you see that we have two studies right here below with p-value below 0.05. But let's look at here. These two studies, Gillis and Di Mario, you have the p-value is around 0.336 and 0.218 respectively, which are over 0.05. That means if you remove one of these studies, our results will not be significant anymore. So the point of performing sensitive analysis is to identify the study that when you remove that study, it will affect the final result of the meta-analysis, because we will make our risk ratios not significant anymore.
For example, you can see the basis analysis here. Then you one study remove this button here. You can see the effect size is almost the same. So this b value here, that means the horn analysis removing only this single study. Do you understand? So the second one is the horn meta-analysis removing this study. That means you combine this, the first, the third, and the fourth. So that you get this result. Okay. So another analysis is cumulative analysis, but we rarely use it because, for example, you can combine from the smallest sample size to the largest sample size to prove that until, for example, until 10 smallest study can get the significant result. After those study, you don't need the last study. Another one is you use the publication years. For example, it's started from 20 years ago, then 10 years later, you have a significant result. After 10 years, you don't need to perform more clinical trials. That's the meaningful of cumulative analysis. But we rarely use this analysis. Another notification is you have to remember that one study removed you can only use for a significant result. If you have a negative result, no significant, you don't have to perform removing one study, because if you remove it, yes, it's meaningless.
So I have just represented some basic knowledge that you need to perform a meta-analysis for your study. Do you have any question that you want to ask? I think that the most frustrating thing in performing a meta-analysis that I experienced is that you have to choose the suitable subgroup for each study, because, for example, in this study you have they place the time of follow-up 1 year, 24 hours, 30 days, 1 year, and 4.6 years. But in our study, the way they divide their study into different phases is different. For example, this study right here, 38 months. Where I will put 38 months in my for example, I want to compare 12 months, 24 months, and 3 years, 4 years, but this is 38 months. It's completely different. So it's really hard to put the risk ratio together when a lot of our studies has different kind of time of follow-up. So actually, we have figured out a solution for that in our study 135 and 02. We use this kind of effect size. We use the what's this one? Okay, we use the rate evens by person year, unmatched group, and person years in each group. Okay. So this is more a little bit advanced, but I want to introduce talk a little bit about it. What's the even rate? What's the person years? So basically, the person years is is some kind of adjustment that you want to perform in order to consider the different kind of time point. For example, in the event right here, we have 7 deaths, 7 deaths over 111 cases with a 1 year of follow-up. So what I want to do here to calculate the person years is I want to multiply the total number of population to the time of the time of follow-up. For example, in this situation, we have 38 months. I don't know if 38 months is how can we I don't, if we perform a traditional meta-analysis with a subgroup analysis, I don't know where to put 38 months into my into where I want to perform the analysis. But in this situation, you can take the 38 months, divide it by 24, and you get the 1.550, something like that. And that's the years. For example, 1.56 years, and you multiply it with the total of the population. This means that when the longer you observe, you put the observation on the population, the person years will increase with the more cluster you included in the population, and the more time you observe them, then the person years will increase right here. And when you put them, you don't have to worry about choosing the subgroup within study, different kind of time of follow-ups. That's what we perform in S135.2. But the weakness of this is only applied for the time of follow-up with different kind of time, because you can multiply the time with the total of the population. But when your subgroup within study is something like, type A, type B, different type of intervention, then I think we just stick with the traditional subgroup analysis. I want to talk a little bit about another study. The data of this study is kind of different to the traditional one, event and total population. In this study, we investigate the effect of 2 different kinds of drugs, toracemic and toracemides and furosemides. These 2 diuretic drugs. So we want to investigate the effect of these 2 drugs on the blood pressures. In this situation, the diastolic blood pressure. We extract the data before and after using the drugs, and extract the data of blood pressure, diastolic blood pressure before and after using the drugs. So you can see here is, for example, in the first study, Ferrara 19 and 97, we compare the toracemides 10 milligram per day and to furosemide 25 milligram per day. The total sample size of the first group with toracemide is 20, and the total sample size of the second group is 20. We have the before using toracemides, the blood pressure, the mean blood pressure on the population is 83, and the standard deviation SD is 11.8. After using the drugs, the post-treatment mean is 81. So you see that there is a decrease in the diastolic blood pressure from 38 to 31, from 83 to 81. We have the same thing happen in the furosemide group, 78 to 79. So they don't, it's not decrease, instead it's increase, it even increase. So what we want to do here is we want to compare which drugs, toracemide or furosemide, has the more impact in decreasing the diastolic blood pressure. The effect size I use in this situation is not the dichotomous, because this is not dichotomous variables. This is the kind of data that we call is continuous with means. We choose matched group or unmatched group. We chose unmatched group because we have two groups, toracemide and furosemide, and in this we choose mean SD pre and post. Again, pre and post treatment, and the total number of population in this group. So right now, after choosing that effect size, we have a table like this with this column. Insert the number. One of the things that I want to mention here is the effect direction. You will say that some study in somebody I choose the effect direction as negative, but some in somebody I choose as positive. How can we decide when we want to choose? We want to the effect size to be negative and when to be positive. I mean, you have to you have to understand the meaning of these kinds of effect direction. For example, toracemide decrease the blood pressure from 83 to 81, so it's degree 2. But for furosemide, is instead increase the diastolic blood pressure from 78 to 79, increases by 1. So the effect we want to investigate here is the decreasing effect. So toracemide had the blood pressure to decrease by 2 millimeter mercury, but the furosemide increases, so we have to consider this as a negative for furosemide. It means -1 because it increase it goes against the effects that we want to investigate. So the value for this is -1. So let's do -1 is 3 in total. You can see here a difference in mean is 3 in total. -3 is on the same. If you choose this as positive, then in the after you run the analysis, difference means the difference means scale. So you can see that toracemide in the first study, toracemide is better than furosemide in decreasing the diastolic blood pressure. So the effect size, the difference in mean most clinching to the size of thoracenamide. So we have to set the effect direction so that in the forest plot, the difference mean clinching to the side of thoracenamide. In this case, it's to the left. And in another example, for example, I want to take this partner S, another study, the third study here. You see that the blood pressure after using thoracenamide is decreased from 82 to 74, and the blood pressure after using furosemide decreased from 83 to 72. 83 to 72 is 11 millimeter mercury, and 82 to 74 is how much? 8 millimeter mercury. So you see that furosemide is better in this situation. So you have to set the effect direction towards the side of furosemide. In this situation, you have to test it positive, because in the forest plot, yes, the difference it means will reach into the side of furosemide, which means the furosemide in this study is better than furosemide in this study is better than thoracenamide. That's the meaning of effect directions. About the pre-post correlation, I have at the first time I performed the analysis for this study, I also did not understand what the meaning of pre-post correlation. But
cái pre-post correlation này mình có thể set ở 0.5.
0.5.
Nếu như cái nghiên cứu đó không có thì mình
if your study do not contain the pre-post correlation, you can set it as 0.5, but you have to mention it in your systematic review. You have to mention it in the reserve part. So after performing the analysis, the heterogeneity is below 50 and the p-value is over 0.1. So let's take the fix. Let's take the fixed effect model. The p-value here is 0.94, which is not significant, so we don't have to perform the sensitive analysis with one study removed.
Anh nói không biết được không? Mấy bạn không nghe thấy, nếu mà dùng mic mấy bạn nhắn tin nói to lên. Còn cái này quay vô đây để em quay cả màn hình này luôn. Thì mình tương tác màn hình thì chính các bạn sẽ thấy, còn những cái màn hình nào các bạn không thấy thì sẽ thấy ở đằng sau. Đây là quay cái này.
Okay.
Nói to nha.
So we don't have to perform the sensitive analysis in this situation because the p-value here is not significant. However, we have difference mean is 0.04, pinching to the side of furosemide. In this situation, furosemide is better.
Nói không có mic. Không có mic luôn á. Mấy bạn kia là có mic không nghe được.
In this situation, furosemide is better than thoracenamide because the effect clinching, the difference in means clinching to the side of furosemide. But actually, you can see that the difference in mean is very small. The p-value is not significant, so the result is not significant. So that is an example for performing a meta-analysis with this kind of continuous variables, continuous data. You can apply it if your study do not have the traditional data with the event and total people of total number of the population. Do you have any question regarding this meta-analysis?
nice presentation. So now I'm moving to another part. My experience on some issues. Perhaps Thanh didn't present the subgroup analysis. So it's that time to find my file. So you can take 5 minute break. Is it okay?